Hello and welcome. Today I'd like to talk to you about working with DICOM. My name is Mohamed Hussein, and before I get started, I just want to remind you that I may not be able to keep up with the comments on YouTube. So if you have a question, please feel free to use my email. My email will be shown on the last slide of today's presentation. Without further ado, this is the plan for what we're going to be doing today. So very quickly introduce myself. We're going to cover some basics of DICOM. From there, we're going to talk about DICOM Communication. We go on to talk about the new mode of DICOM Communication, which is DICOMweb. And then what's it like to be working with DICOM? Some common things to keep in mind for doing this. So this is myself. I'm an independent consultant in medical imaging. I've started working in this field in 2010. I'm a software developer by training, so this is kind of how I view the world. I apologize if I make any assumptions in this presentation that pertain to software developers but don't apply to other professions. I'm involved in the imaging community like Society of Imaging Informatics, RSNA, which is Radiological Society of North America, and I'm also a proud member of the open source community. So without further ado, what is DICOM? Hopefully, if you've arrived at this video, you have a little bit of an idea, but in case you don't, we'll cover some basics here. So DICOM is Digital Imaging and Communication in Medicine. And it's very important to focus on every word in that sentence or that acronym, imaging, communication in medicine. And the communication part is very important. So what does it actually mean? Well, the DICOM standard is the de facto standard used in a lot of specialties, especially in medical imaging and especially radiology within medical imaging. It is a massive standard. I believe something about 7,000 pages or more. So in my line of business, it's always funny when the new guy hears about DICOM and says, yeah, I'm going to go read the standard. They're not going to read 7,000 pages. So usually what people do is people will usually read parts of the standard that pertains to the work they do because DICOM covers a lot of ground. Another thing that's important to know about DICOM is that DICOM is a standard which is backwards compatible all the way to its inception, which is in the 1990s. Now, it doesn't mean that it doesn't change. The standard is constantly evolving. New parts are being added to the standard and some parts get retired, but overall it's maintained some backwards compatibility, which is very different from what you see, for example, with things like HL7. So if you've played with DICOM, most likely what you've seen are these .dcm files. So these are the files, how DICOM is actually persisted on disk. Okay, we'll be talking about that in a bit more in details, what that actually means. But that's sometimes called DICOM Part 10 file because Part 10 of the standard is what describes how that format is actually persisted on disk. Now, if you look at the right, you're going to see an example, quote unquote, dump from a DICOM file. And that dump basically shows you a bunch of numbers followed by an attribute name and then its value. So this first part is called a tag. So 0008, 0005, that's the tag ID in this particular case. These tags are actually made up of two parts. The first part is actually the group, as it's called. And then the way that these tags come together is usually governed by what's called modules. So you may have like a patient module that keeps information about the patient. You may have an image module. You may have a module specific to CT scanners versus MRI scanners and so on and so forth. Now, if you scroll through this very quickly here, you're going to see some interesting things. Like, for example, modality is CT. The manufacturer of the modality here is GE Medical Systems. And in here, there's the model name. So this is the name of the scanner that actually produces this image. So this is a really cool thing about DICOM. And you'll also notice that the things stored here are a mixture of things. So for example, here is a date, there's a time, there are strings. So each one of these tags can have what's called a value multiplicity, which is how many values exist within it. So if you take the example of image type over here, you notice it says original, /primary, /axial. In this case, this is actually a value multiplicity of 3. So this attribute actually has 3 values: original, primary, axial. The backslash is the delimiter of multiple values here. Now, what you don't see here, because this view doesn't show it, is that each one of these tags also has a value representation. If you're a programmer, that's basically the data type. Now, the data types in DICOM don't necessarily map directly to programming data types, but they're pretty close. So you can have types like a date, and in this case, that's the way the DICOM way of storing dates. So it's year, month, day, without any separators. And then time is the same thing. It's stored as hour, minute, second, without any separators. Do watch out that time in DICOM is actually stored as a float, so you can actually have decimals in there. Not commonly seen, but it's there. And then the other thing in DICOM is this concept of UID. So it's these series of numbers that are separated by dots. These UIDs are what basically was invented in the 90s that is analogous to GUIDs nowadays. So nowadays, a lot of people are used to seeing these blobs of letters and numbers that are separated by dashes called GUIDs. UIDs in DICOM are similar, and basically it just stands for unique ID. So there are multiple value representations in DICOM. There could be codes, there could be short strings, there could be long strings. I'm not going to get into the details, but you get the picture. Now, one thing you may or may not be able to tell here is that DICOM, the way it was actually created, was really built around a time when human beings did a lot of storage on slow storage devices, exceptionally slow storage devices like tape. And in this case, being able to do sequential reading and being able to calculate how many bytes you want to jump ahead to get to something specific was very important. And that's one of the reasons why DICOM looks the way it does today. The other thing you don't see in the dump on the right is that at the bottom of this, there will be a tag called pixel data, and that tag would contain binary image. So the 2 bits of this file, so the whole file is in binary. The first part of the file is the header, kind of what you see here on the right. And then the second part would be the pixel data. Now that pixel data is literally an image, and that image could be uncompressed or it could be compressed. And if it is compressed, just like any other image on the web, it could be compressed in a multitude of formats. So for example, it could be something like JPEG 2000, it could be JPEG LS, it could be other compressions, it could even be other image formats. It could be potentially a PNG or a TIF or something like that. If you were to pick up a DICOM image for processing, in addition to the pixel data of that DICOM file, you may actually find yourself interested in a number of attributes that give you a little bit more information about it. I don't want to get into a lot of details here because the attributes of interest will differ depending on the use case, but I'll walk through a number of things. Something like acquisition date and time tells you exactly when an image was acquired. That might be useful from a sorting point of view as to which image was captured first and which image was captured last, just as a random example. You see here is bits allocated, and that's actually one of the cool, unique things about DICOM. A lot of the times the images that are captured in DICOM are typically 12 or 16 bit, which is very different from like the typical pictures that you see on the internet or pictures that you take with your cell phone, which generally happen to be 8 bits. So that's one of the interesting things about DICOM. People don't appreciate the work that goes into displaying DICOM images because you gotta convert from this high fidelity format into lower fidelity to be done on the screen. But by preserving the high fidelity here, you actually preserve a lot of details that otherwise could be lost. So in this particular case, this one image is 16 bits and it's telling you that the high bit is 15. For programmers in the room, this is basically, essentially a question of little Indian versus big Indian. If you're not sure what that means, feel free to Google it. Photometric interpretation tells you if this image, essentially at a very high level, if it's black and white or color, and if it's black and white, what kind. So monochrome 2 is the type here. I don't want to get into a lot of details. Columns and rows are the DICOM tags for height and width. So in this case, my image is 512 pixels by 512 pixels. We talked about manufacturer. We talked about the model name. You also see that there's a version in here too. There's some information about the image and the exam that was captured, the procedure. So in this case, it's a CT chest. It was the lung. You may get some information like slice location, thickness, window center, window width. These are all information you could use to process the images properly, whether you're processing them for machine learning or you're processing them for viewing. These are all very useful bits of information. So the images or the modalities that create DICOM can be a wide variety of things. These are usually denoted by something called a subclass UID. So something that you saw highlighted in my previous slide. So there's a subclass UID, which basically communicates the media type. Like if you were using web-based APIs, it's the equivalent of a MIME type as an example. So subclasses, there's a list of them that you can look up online if you wanted. A bunch of them are image types and a bunch of them are non-image types. So essentially more metadata objects. We'll cover those in a moment. If you are looking at image types, usually the biggest difference is the physics of how these images are captured. So you have X-ray and CT, which actually use X-ray. So CT is essentially portable, well, not portable, it's moving X-ray. So it's capturing multiple images that are then presented as slices. MRI is magnetic resonance imaging, which is again magnets. So there's, X-ray is essentially rays of light versus magnets. So X-ray and CT actually will give the patient some radiation exposure, whereas MRI has no radiation exposure. So for example, pregnant woman is more likely to be sent to MRI or even ultrasound, which uses sound waves, to get scanned than a pregnant woman is likely to be sent for something like a CT scan. Now, there are other modalities coming on board. There are also other specialties beyond radiology that use different machines and apparatus to take pictures. But generally speaking, at a very high level, this is what it looks like. And on the right-hand side, you see here's a sample chest X-ray. Here's a sample of a abdominal CT scan. And here's an example of a breast MRI exam. So just to give you an idea of what these images look like. Now, a lot of the time you may hear people talking about 2D versus 3D images. 3D images are the ones that are captured as a slice. So if you imagine kind of like if I'm being scanned, if they're scanning my chest, then it's kind of taking slices across my chest going up all the way. So then these can be constructed into a 3D image and then processed accordingly, versus something like a chest X-ray, which is just a single picture and that's it. It's almost like the concept of capturing a movie on your phone versus a single picture. So we talked about non-image types. Here are some examples of what could be. So key object selection is something that is used to denote, as an example, images of interest. So for example, if the radiologist wants to show the referring doctor of the 500 slices in that CT scan, which ones are the ones where they see an obvious issue, they could put these in a group called a key object selection, and then that would be much easier for the doctor down the line to be able to find that. These could also be done to flag the opposite. So images that are flagged for quality reasons or images that are flagged for review could be one. GSPS objects are another one. So that's a dynamic way of storing markup. So instead of burning the markup into the image pixels, it can be stored separately, essentially kind of like in a vector format, and they can display it on top of the image laid out in real time. Structured reports are a whole ecosystem of their own within DICOM. They have a lot of uses. One of the uses is computer-aided measurements, so CAD. Some machines are capable of performing some measurements. Machines that produce radiation, especially CT scanners, can produce dose reports in SR. And of course, with the advent of AI, structured reports are one of the prime methods of communicating findings from an AI model to the rest of the healthcare systems involved, such as PACS, EMR, etc. You can actually embed documents into DICOM. DICOM can, in theory, encapsulate just about anything: PDF, Word document, PowerPoint, etc. And of course, you can embed videos into DICOM as well. It is very important. We give a lot of examples that pertain to radiology, but it is very important that you remember DICOM is not just radiology. There are other specialties that use DICOM, and more are coming on board as we speak. So the closest one to radiology is actually cardiology. They use some of the modalities which are in common with radiology, for example, like ultrasounds. But then cardiology also has things like ECGs or EKGs, which is what you see here. These are actually not stored in image format, but rather actually stored in a metadata format and rendered on the fly. You have specialties like pathology, and they're pretty special because they have massive images, dermatology, and of course wound care. So for example, specialties like dermatology in the past may have just used cameras and kept their files on disk in JPEGs and whatnot, but they're now starting to work about digitizing this, and the idea of creating a comprehensive patient record is something that's definitely taking off right now. Sometimes you hear people calling it enterprise imaging. That's basically what it is. It's the idea of bringing the entire patient record, all their images, everything is in one place, so it's easily found. So we talked before about the two components of a DICOM image. If you wanted to create your own DICOM file or object, whatever you want to call it, really what you need are the two parts you see in yellow. So you need a header and you need pixel data. So for the header, you'll want to go and find out mandatory attributes that you have to have. So we talked about the UIDs. Typically there are UIDs at multiple levels in DICOM. So there's a study UID, there's a series UID, and a SOP UID. These are mandatory. And then other attributes you could add that are optional. So patient attributes, for example, you could add a patient name if you wanted. You could add a patient date of birth. You can add patient sex, so on and so forth. And then you can also add information about the image, kind of like what you've seen before. So the rows, columns, etc. Now, rows and columns are actually mandatory in this case, but other examples like window width, window center are two examples of things that you could choose to embed if they apply. And then you embed the actual image itself, so the pixel data. So that image, again, is binary. Say, for example, it's JPEG. If it is compressed, you can store an uncompressed image, essentially a bitmap into DICOM. Obviously not very highly recommended because of space constraints. Now, when you do compress an image, there is always a choice of using a lossless compression or a lossy compression. And then if you do use a lossy compression, it's a question of how much loss are you willing to tolerate. The type of image will determine the subclass UID, which again is essentially the media type. So really, if you wanted to write code to create a DICOM file, these are essentially the two things you want to do. You just need to write the exact lines of code to take care of each one of these individually. Moving on to DICOM communication. So remember what I said about DICOM Part 10 files? That's typically a lot of people, when they first exposed to DICOM, that's what they see. They see DICOM Part 10 files, and they assume that this is DICOM, that maybe people are emailing these files back and forth, or we're putting them on shared drives or something. We're absolutely not. There's some pretty serious chatter happening in the DICOM world between devices as they work these things through. That's all part of the standard. So typically what you have involved in a given hospital or clinic is that you have a bunch of modalities or some kind of capture device. So modalities like X-rays, CT scanners, capture devices, say for example, if it was cardiology, you might be capturing those ECGs that we talked about. And then you have an image manager, which is kind of like a general umbrella term for basically a system that manages storing DICOM files, and it's kind of like the hub and the source of truth. So these capturing devices capture images, and then they send them to the image managers, and then the image managers kind of own them from now on, and then these images have a life of their own. The most typical image manager you'll see is a PAC system, which stands for Picture Archiving and Communication System, or a VNA, which is a vendor neutral archive. I don't have the time to get into the nitty-gritty details of what the differences are between these two, so I'll let you Google this, or if it isn't clear, feel free to email me. And then at the very end, we have basically the consumption of these DICOM files, which is generally the human beings. So clients, now that could be AI. AI could be retrieving these images to do some analysis. But right now, the most typical use case are human beings. So usually images are read by a radiologist, they create a report, but then other doctors may be interested in seeing them. Like for example, if it was your family doctor who referred you for the exam, they may actually want to pull it up and be able to see some things for themselves, in addition to what the radiologist said or saw, and they may choose to show you. Same thing for like an emergency room physician, and so on and so forth. So DICOM communication in the real world is typically done with a protocol called DIMSE. DIMSE is very DICOM specific, and DIMSE is TCP/IP. Now it is built as another layer on top of TCP/IP. The way it works is you define something called a service class user and a service class provider. These very loosely map to the concept of a client and a server, but not exactly, because a system isn't always an SCU or always an SCP. It can actually wear multiple hats. Okay, so for example, if I am one actor that can send DICOM images but then can receive them, then in one scenario I might be an SCU, and in another scenario I might be an SCP. In DIMSE, two applications basically perform a handshake, and that handshake is usually performed using AETs, which is an application entity title. Long story short is basically, because this is from the 90s, the way of establishing trust was, if you know my name and I know your name, that means we know each other and therefore we could talk. So it's kind of like human beings in a way or another. If you get an email from somebody you know, you're likely to trust them. And then of course, transfer to syntax is the next thing that happens, which is basically to say, here is what I'm about to send you. Tell me if this is something you can actually work with. And again, if you're using the analogy of email, if I know that you only speak English, I'd rather be sending you emails in English, because if I sent you emails in Arabic, you probably wouldn't understand that very well. So thanks to my friend Brad Jenner for these slides. At a high level, imagine if you went to the hospital or a clinic, say for example, you're coughing. You're seen by the emergency room doctor, who decides, well, I can't really conclusively tell what's going on. We should get an image of what's happening inside. Let's get an X-ray. So they create an order for an X-ray or a CT scan or whatever. Somebody in the radiology department will review that order, determine its appropriateness, tweak the details of the order as needed to make sure that they get optimal results. And then that order is performed, which basically means you go into the scanner or next to the scanner, they capture these images. These images are stored in the PAC system. The radiologist will then go in and read those images, so basically analyze them, and then they create a written report that describes all the things they've seen. That report is created and then distributed to everybody else. So in this particular case, it would have gone back to that ER doctor that created the order, and then the ER doctor will discuss these results with you. Now, at a very loose high level, not all of these steps are actually DICOM. In fact, really, mainly, it's the one particular step of capturing these images that is DICOM based. And of course, then the radiologist, when they read them, they're actually consuming DICOM. Everything else is actually handled outside of DICOM. Now, this is to say that DICOM is a small part of the flow, but an integral part of the flow, because without DICOM and imaging, the vast majority of healthcare wouldn't work. And as a patient, you probably know that a lot of the time when you go see the doctor, imaging is one of the first tools in their chest that they reach out to. So let's go get some images, get some CT scan, get an MRI scan, get an ultrasound. So it's very, very typical. If DICOM devices were two teenagers chatting, this is basically what their chat logs would look like. So in this case, the modality, denoted by this radioactive symbol, goes to PACS. And remember what I said about AE titles. So that's how they're greeting each other by name. So hi PACS 123, I am modality 987. And the PACS says, hey, I recognize your name. That means we can talk. Remember, this is security from the 90s. It's probably not amazing, but that's what it actually looks like in real life. Modality says, I want to send you images for this particular patient, and they are encoded in JPEG LS. So in this case, I provided the context of the patient record, and I've provided context of what it is I'm about to send. The PAC system says, I recognize JPEG LS, so yeah, that's good to go. Let's go ahead and do it. Modality sends the actual objects, and again, these DICOM objects look like what you've seen before. There's the header, which has metadata, and then the image pixel data. When the transaction and all that transmission is done, PACS sends a message to the modality saying acknowledge, and the transaction is done. So that is a very high level how DICOM DIMSE works. It is a bit of a chatty protocol. I'm not showing you all the nitty-gritty details, but there's a lot of back and forth in DICOM DIMSE. It's also important to know that within DICOM, there's a hierarchy. At the top, there's a patient with two asterisks here because it's kind of like a weird level that kind of exists but not really exist. The first real level is actually the studies. So in this case, we're imagining a patient that has two studies. There's an MR study and an RCT study. So the MR study, usually these studies have something called a localizer. I'm not going to get into the terminology. and then you actually have the sequence of images that were captured. So in this particular case, there's a series, which is the localizers, happens to only have one localizer. And then the sequence, I'm pretending there's only one sequence series. Sometimes it's usually more than one. And this can have any number of images, so 1 to n. Similar to the CT scan, CT scans usually have localizers, but for simplicity, I've ignored that part. They'll have a sequence, usually more than one. But the cool thing about CT studies is that you're going to have a dose report, which is usually coming across as a DICOM structured report. So here it's in its own series, and as you can see, there's a structured report with dose information. At every level in the DICOM, there are a number of metadata elements that are of interest. I don't want to go through these in a lot of detail, but here you get an idea of what they're like. Feel free to go Google each one of these to find out a little bit more about them and what they're used for. And now we talk about DICOMweb. I don't want to get into a lot of details of DICOMweb, but very quickly I'm going to cover. So in traditional DICOM, you usually perform a C-suite of transactions. And in this case, the C-suite is not the business term, it's the DICOM term. So to find something, to look or search for something, you use a C-find. So if you want to find all the studies for patient XYZ, you issue a C-find for patient XYZ. If you want to search for studies that are performed on January 1st, 2023, use a C-find to do that. In DICOMweb, you use an interface called Keto RS, and you notice a lot of these have the word RS, which stands for RESTful service. So DICOMweb is actually a RESTful service, which, if you compare it to DICOM DIMSE, is a lot less chatter and a lot less back and forth. It's more like you perform a request, you get your result. Perform a request, you get your result. It's not a lot of back and forth chatter. In traditional DICOM, if you wanted to ask for some images, you issue either a CMove request or you perform a CGET. So that's the way you can retrieve images. I'm not going to get into the difference between the two, but in DICOMweb, you have WADO RS, which is the newest, latest, greatest standard, but then you have an older standard called WADO URI, which is at this point maybe a little bit more common because it came out a long time ago, but I certainly encourage you to go the WADO RS way because it's the way of the future. If you're a modality that wants to send images into the system, in DIMSE, you would have used CSTOR, and in DICOMweb, you use STORS. Now, I talked about the chatter difference. So if you remember the previous slide with the chatter back and forth, this is kind of what it would look like for DICOMweb. Let's say, for example, the doctor here is using a viewer and basically just wants to see the studies for accession 1, 2, 3, any studies matching that accession. Hopefully it's just one. But yeah, that's what they do. And then behind the scenes, the PACS system sends XML or JSON, you could talk both, back to the viewer with some information. So here we see things like study date, there's an accession number, 1, 2, 3, that matches. It's a modality of CR, which is X-ray. Series description is say chest PA, patient is XYZ, and so on and so forth. This is a very shortened example, but it's just there to give you the gist of it. One thing I want to talk to you about, and this is important to talk about, we kind of made a little bit of fun of DICOM DIMSE security being based on AE titles. It's actually not fair to leave it there, because what happens is in DICOM DIMSE, you have the option of using certificates to secure your services. However, unfortunately, in the real world, it's almost never used. DICOMweb is RESTful based, which means it works across HTTP and HTTPS. Now we know that HTTPS is very prevalent, so hopefully more and more people will be implementing the secure version. And then additionally, as far as authentication authorization, DICOM standard actually stays out of that. That's actually left for the implementers to decide, because the decision was there are already multiple standard bodies that look after authentication authorization. There's no reason for us to duplicate the work. Instead, we just leave that work for these specialized tools, and then they do it. So that's why you have a plethora of options. It could be simple username and password. It could be something like OAuth. It could be other things. I'm not going to get into the details. Hopefully you can Google these things and find out more about them. So now if you want to pick up your toolbox and development chops and you want to start working with DICOM, how do you actually go about doing that? Well, I'm not going to show you a code example today, but I'll give you some tips that I myself have learned some of these the hard way. Number one, Do not reinvent the wheel. You might be tempted to try and do yourself in DICOM. I highly do not recommend you do that. Always use a toolkit. There are toolkits which are command line based. So for like quick things that you want to check or get a DICOM dump or modify the header, you could use the command line. Or if you want something that's repeatable, you want to write it into a script or an application, there are plenty of code libraries, SDKs for different languages. And I'm going to give you some examples in the next slide. I'll also even take this advice as far as saying that if you find yourself managing a lot of DICOM files, say you're in the middle of a research project or something, instead of storing these files on files and directories in your file system, I would actually recommend taking a little bit of time to stage an open source PACS implementation and use that to manage your DICOM files. And you will thank yourself down the road because it just makes that much more sense. Be careful of observer bias. Again, a lot of people come into this domain, they get dumped this bunch of DICOM.dcm files and assume that's what DICOM is all about. Again, DICOM objects, studies, series are not static objects. They actually have a life of their own. Studies can be merged, studies can be split, images can be removed for quality reasons, etc. Patient demographics are sometimes updated. Sometimes you get a patient that's admitted into the ER with, let's say, car accident trauma. So they actually have no idea who that patient is. They're entered as Jane Doe, but then they realize down the line that no, that actually was Amanda Wilson, for example. So then all these objects are updated with the new patient demographics. So just because you were giving a static copy doesn't mean that the originals haven't moved on past what you see. And of course, remember that DICOM standard is constantly evolving. They're always adding new data types. They're always adding image compression. They're always adding other things. So it's very important that when you're writing code to deal with DICOM to have very good error handling. If I may drop a keyword here, I would say defensive programming is your best friend when it comes to working with DICOM. So I don't want to go through these in a lot of details, but for programming languages, there's at least one for every language to do things with DICOM. So Python has PyDICOM, PyNet DICOM. One is for dealing with DICOM files. The other one is for dealing with DICOM connectivity. JavaScript has DCM.js, and then Cornerstone is one library you could use for viewing and rendering images. Java has the venerable DCM4Che library. .NET has Fellow Oak. There are command line tools like DCM-TK, DCM4Che. These are, again, quick, easy command line tools you can use to dump an object, dump the pixel data, and so on and so forth. I always have these handy, and I recommend you do have them as well. There are a ton of utilities you could use to play with DICOM on your computer, from DVTK, which has things like editors that are actually GUI based, to viewers like Horus for Mac and MicroDICOM for Windows, to mini PACS implementations like Orthanc, ClearCanvas, Conquest, XNAT, and then other viewers that are web-based like the OHIP viewer. There's no shortage of DICOM tools you could use out there that make it really, really easy for you to achieve what you're setting out to do. That is everything I wanted to cover today. Again, thank you for your time. Thank you for being here. And please use my email address that you see on the screen to send any questions. I can't promise to be able to stay on top of the comments on YouTube. Thank you one more time, and good luck playing with DICOM.